So without any further ado, I will introduce Kevin, who I've known for many, many years. I think it's at least 10. Kevin joined the railways in 2000 as a graduate, a company called AEA, then going into Network Rail in 2006. And since then, it's been involved with leading data collection changes throughout Network Rail with things such as the introduction of the ground penetrating radar data systems. And now he's a technical and engineering lead in Network Rail's IM program. So Kev, if you're ready, I'll look to hand over to you.
Okay, thanks, Tom. Thanks for the introduction, and yeah, thanks everybody for sort of joining, and looking forward to talking to you tonight about infrastructure monitoring. A subject that's close to my heart, something I've been involved in my whole career. So yeah, sort of 23 years and counting. Do apologise if there's black boxes appear on the presentation. I'm sort of IT and Zoom particularly not clearly my strong point. So all being well, bear with me, and we'll be able to get through the presentation. Okay, so is that all working and sharing and slides changing?
Yep, all good, Kev.
Okay, good. So yeah, brief sort of introduction in terms of what I'm going to cover tonight. So bit of a rewind, sort of set the presentation in context. So going to go back a bit in time and look at some of the sort of where we've come from, some of the sort of historic infrastructure monitoring things that I've managed to collate over my time. Going to consider some of the key drivers for change. So mainly during the course of my involvement, big events that have caused fundamental changes to the way we monitor our infrastructure. I'm going to jump into the program I'm currently working on, which are our infrastructure monitoring program. So fast forward to the next sort of last couple of years, cover some of the changes that have happened in that time period. And then finally, just going to conclude with a look ahead to CP7 and beyond. So what's on the horizon, just to sort of bring that to life a little bit and give you a taster for what's coming up. So to start off with, probably bored of my voice already, but just going to start off with a video. So here it goes.
For a story well off the beaten track, we're taking you along the London Reading line, where British Railways are trying out a coach of unusual design. It's what its French builders call a detective coach, which investigates all irregularities on the tracks. Brought over from the continent, the coach is fitted with a multiple recording machine, which can give 7 simultaneous answers to 7 separate questions. The answers are in the form of graphs drawn by delicate stylus pens, which are connected through a sensitive wire and pulley system to the coach's axles. Feeler discs relay a picture of the track direct from the rails themselves. Changes in the track can be checked by comparing records of previous tests with the one actually being made. In order to test the accuracy of the new track recording coach, a 20-year-old portable machine is installed on board. The advantage of this model is that it can be used in any coach. Its disadvantage, that since each coach has its own peculiarities, its readings can never be constant. These tests will show whether it's time for the old type gear to be replaced.
So apologies for the sort of picture quality there, but yeah, like that video sort of just sort of sets things in context. The dramatic music sort of adds to that as well. So yeah, we're going to refer back a little bit to that. Yeah, even though the video, I'm not quite sure when it's from, but a number of years ago, definite points to pick up on that I will pick up on in the presentation. So starting with coaches of an unusual design. A couple of examples here. The one on the left, the Porcupine train. Both these trains were used on the network for structure gauge measurements, so making sure clearances between rail vehicles and the infrastructure is maintained. Probably don't need to say, or hopefully don't need to say, didn't have any sort of first-hand experience of the one on the left, but very much did have experience of the one on the right. I think the Porcupine vehicle would be a very much a struggle to get through current design, current approvals. But yeah, primitive mechanical system, spikes sticking out that would contact infrastructure as the vehicle passed and determine the clearances to the infrastructure. Similar principle on the right with Network Rail's structure gauging vehicle, our old black box vehicle, as we affectionately called it, converted freight wagon, effectively split, cut down the middle of it for the lights to shine out of, that you can just see there as the vehicle sort of parked under its calibration frame, and cameras looking back, so the lights illuminate the structures as we went along. The cameras look back, and through triangulation principle, the measurements of the offset from track to the structure were measured. Some fond, probably maybe not the right word, but some very warm memories of that vehicle, traveling around the network. Black being a good choice of colour for hot weather, not really, coupled with the halogen lights that were employed to actually light up the structures. It could have been known as a sauna vehicle. It was often 40 degrees plus inside that vehicle, so not a place that you wanted to spend a huge amount of time, but successful nonetheless in terms of collecting data about our infrastructure. Always like to sort of just recap slightly, and apologies, I'm conscious of this black box. Recap at the start of the presentation like this on sort of why do we do monitoring? Why do we monitor our infrastructure? Why do we have these measurement trains that run around the place? So primarily it's safety. So as a picture on the left, key requirement, key sort of driver for doing this is about safety. It's about keeping trains on the track, preventing derailment, reducing the risk of derailment by measuring track condition, track geometry. If we can do that, we can move to the middle picture. So similar safety sort of angle, but this time it's about making sure we're not hitting structures, making sure we're not hitting passing trains by the tracks having got too close together through maintenance activity. And then on the right hand side, if it's an electric train we're talking about, we've got to keep the wires up in the air. So we've got to keep the pantograph in contact with the wire so that the train's drawing the current required to propel it down the track. Obviously, monitoring is carried out for a whole load of other reasons than just for safety. Obviously, a sort of infrastructure asset management purposes, things as mentioned by Tom in the introduction around passenger comfort. It's not just about the safety, but safety is the kind of primary reason for monitoring the infrastructure, and regulatory requirements to do that as well. Over the 20 odd plus years I've been involved in infrastructure monitoring, there's never a dull moment, never been a dull moment. I remember one of the first trips out on one of the measurement trains I had. Unfortunately, we managed to hit a herd of cows that had escaped onto the track. So we managed to rip a whole load of our measurement equipment off, damage the locomotive that was hauling the train, and not to mention the damage caused to the 7 cows that didn't make it. But yeah, never a dull moment. I'm going to show you another video, just a short video, again just highlighting the point of things that have happened over the years. So that video shows a sort of particularly painful event in my career. August Bank Holiday 2014, a day etched in my mind, where unfortunately we managed to destroy our only measurement pantographs. So the measurement vehicle, or electrification measurement vehicle, had been out of service for a number of months, years actually. I think in the end, 18 months or so. We just upgraded the measurement equipment, and the vehicle had just started running back in service, just to commission the new system, when it hit a section of track that had recently been maintained, and on its way out of the maintenance activity, one of the RRVs used for that maintenance had hit the OLE without anybody noticing, dislodged one of the registration arms, which meant the wire was put in the wrong position. caused a whole lot of damage to our measurement system, ripped off the instrumentation, fried all the electronics. And this next picture showed the end result, bits of pantograph on the floor of our depot. You can see the nice 90-degree bend in the box section there that actually is supposed to be straight. So huge amount of damage caused to the vehicle, to the pantograph, and to the instrumentation. Can't pass this photo without just pointing out the very ironic red and white tape that I think you can just about read. Fragile, do not crush. Makes me smile every time I see it. Okay, so bit of a sort of look back at some of the things over the years, but just want to pause now for consideration of some of the key drivers of change in infrastructure monitoring over my time involved in this area. Unfortunately, that's usually related to accidents and unfortunately often sort of fatalities. So I'm just going to run through a few examples and things that have happened, and what sort of the response has been and what that's been the catalyst for. So Hatfield happened about 6 weeks after I joined the industry. October 2000, high-speed train travelling north out of King's Cross derailed. 4 people unfortunately lost their lives. The cause for that was rolling contact fatigue, so cracks in the railhead propagating down into the body of the rail. Effectively, the train passed over, the rail broke, the train derailed, and yeah, unfortunately, fatalities resulted. The graph on this slide here just shows the long-standing impact in terms of passenger performance measure, or public performance measure, so trains arriving on time. You can see that Hatfield around 2000, it took about 5 or 6 years to get back up to pre-Hatfield levels with the number of trains arriving on time, just due to the massive amount of effort. Speed restrictions applied on sites similar to where Hatfield was, make sure we understood the condition of our asset, massive re-railing program, just causing huge amounts of delays. The upside, if it's possible to put it in those terms, massive catalyst for improvements in rail testing. So it was responsible for the introduction of our ultrasonic test vehicles. So initially, with 1 vehicle being introduced shortly after Hatfield, we now have a fleet of 5, shown on the picture on the left. Just one example. Consists of, as the name suggests, ultrasonic test equipment. Bottom picture there shows the small wheels in between the train wheels, roller search units with a rubber coating on them, actually contact the wheel as the train moves along at quite slow speed. Water is applied between the wheel and the rail, and sound, as you would with a pregnancy scan, sound fired down into the rail, bounces back to the receiver within the wheel, and obviously if there's anything in its path, a defect or a crack or something for the sound to reflect off, that's captured by the acquisition side of the system, and the depth and position and size determined by the level of reflection. As you can see on the diagram there, a number of sensors within each of those wheels, 9 in total, looking for a number of different types of defects, which I'm just going to just give some information on now. So yeah, lots of different types of defects occurring at different angles and therefore detected by different probes. So defects in the head, this is absolutely the cause of the Hatfield disaster. So rolling contact fatigue, cracks in the head, propagating down into the body of the rail and causing a break. Foot defects, the next category, something that's actually really difficult to detect. As you can see on the picture in the middle, that tiny black speck is the actual defect that resulted in a rail break. So you can imagine firing sound down into the rail from the head all the way down to the foot to then spot something that small is particularly difficult, especially if it's not directly within the sort of path that the sound will take. This example just borderline in terms of whether the sound would actually reach it or not. Other types of defects around welds, so either defective welds or defects within welds causing breaks. And then the other main category is around joints. So star cracks, as the name, as the sort of picture shows on the left, around joints where cracks propagate from the holes around sort of fish-plated joints. And in the example there, quite a large section of rail broken away from, so meaning there'd be a big sort of impact as any vehicle passed over that section of track. Just to kind of add to our ultrasonic vehicle and the capability that those vehicles have, we added eddy current technology to measure the surface cracks, so the types of things that were ultimately responsible for Hatfield. That was added around 2010, probably took 3-4 years to actually embed into use. So it's effectively an additional wheel that sits alongside the ultrasonic system. So on the right, at the bottom picture, you have the ultrasonic wheel. On the left, you've got the eddy current wheel. Different technology, as the name suggests, 10 probes spread across the head of the rail, looking for those cracks at different portions of the rail. Effectively an electrical system, so inducing a current in the rail head and measuring the response. Any crack within the sort of area of influence of the system disturbs the field, and the level of disturbance is measured. So this system replaced manual eddy current testing, so people on their hands and knees, effectively with a ruler, measuring the length of cracks within each yard of track and the maximum length of the maximum crack length within a given yard of track to categorize whether the cracking was severe or light. The eddy current system actually measures the depth of the crack. So rather than the length, it's measuring the actual thing you're interested in. So how deep is the crack propagating? And just worth mentioning that, you know, eddy current and ultrasonics, very complementary technologies. The eddy current's really good at measuring down to a depth of about 5-6 millimeters. The ultrasonic equipment is not very good at measuring that first 5 or 6 millimeters, but is very good at measuring for defects within the remainder of the rail. So together, you've got a complete understanding of the health of your rail. This is the kind of so what graph. It's reduction in broken rails. So the history, starting on the left, pre-Hatfield, 900 plus rail breaks per year. Difficult to believe, but actually 900 breaks per year. And you can see as you move to the right hand side, the last 5 or 6 years, average less than 100 breaks per year. So massive 90% almost reduction in the number of rail breaks that have occurred over that sort of 20-year period. You know, largely driven by sort of Hatfield. Overlaid on the graph, making it a bit busy now, I appreciate, but some of the key activities and some of the key things that sort of contributed to that massive reduction in rail breaks. So some of them are mentioned, the ultrasonic test units, eddy current, but also things like improvement in welding processes, improvement in manufacturing processes, also improvement in train grinding, or sort of introduction, sorry, of train-based grinding. So actually addressing the sort of treatment, removal of those cracks before they become too large, too deep, and before you have to go down a different route of removal or remediation. Initiatives within Network Rail over the last sort of 10 years or so, trying to get numbers down to 50 breaks by 2030 and even down to 30 breaks by 2050. So there are things that our technical authority are working on. It's just worth mentioning, I think, that these sorts of numbers of breaks per year are probably very much best in class. So quite a lot lower than other rail operators. So next is Grey Rig, 2007. So unfortunately, again, another accident with a fatality, member of the public travelling on the vehicle. The issue here, the root cause here was failure of a stretcher bar, so part of the switching crossing. Stretcher bar failed as the train passed over it. The points moved as the train travelled over, and effectively one wheel set went one way and one bogie went one way, sorry, and one bogie went the other way, and caused the train to derail. West Coast Main Line this time. The main sort of outcome or kind of catalyst that was resulted as a result of this accident was introduction or improvements in our way of visually inspecting our infrastructure. So what we termed plain line pattern recognition was born and was implemented. Plain line pattern recognition, as the name suggests, is about inspecting our plain line, our continuously welded rail. So not directly addressing the stretcher bar issue at Greyrig, but I'll come on to a little bit more about S&C visual inspection and the improvements that have been made fairly recently in that area. Just a bit of an overview about plain line pattern recognition. It's there to replace the basic visual inspection, so walking up and down the track, looking for problems. 5 vehicles in our fleet equipped with this technology. Effectively, it's a collection of cameras, high definition line scan cameras. So probably I think 125 mile an hour each of the pixels on the camera is something like 0.8 of a millimeter. So getting a very high definition, very detailed picture of the infrastructure. Coupled with that, laser systems for 3D profiles of objects, particularly around the fastenings. So this system is looking for damaged fastenings, missing fastenings, incorrectly inserted fastenings, and also lasers that are used to profile the ballast, both the ballast shoulders and in between sleepers in the cribs. So identifying areas where there's excess or shortages of ballast. The way the system works is that data is collected on the train, and due to the volumes of data that is collected, is couriered off the train, so physically removed on a hard drive, couriered back to our office in Derby, where it's ingested into the processing system. Algorithms are applied to it to spot the things of interest, so candidates, as we call them in PLPR world, and then a team of examination inspectors review the candidates that are presented, identify are they genuine problems, are they spurious and rejected, and for the genuine problems categorize and assign a severity that then drives what timescale they need to be reported to, and B, how quickly they need to be rectified. And this table just summarizes the types of things that PLPR detects. So, and also describes kind of how those things are detected. There's two main ways of that happening. Firstly is around the PLPR processes, so things that are spotted just by looking at the images or the laser scan data. And the second one is things that are triggered from track geometry data. So track geometry data is processed, faults are identified, and where a fault exists, an image is presented in order to try to understand the root cause of the geometry fault. So whether it's a wet bed, whether it's a rail defect, yeah, the root cause is understood from presenting the image alongside the geometry fault. The next main driver or event that I'm going to talk about briefly, this one is Liverpool Street. So thankfully no fatalities here. 2013 derailment in the throat of Liverpool Street station on the Anglia route. Effectively the fastening system failed, wasn't holding the rail adequately, and as the train passed over, the rails moved because they weren't secured correctly and caused the gauge to spread and the vehicle to drop into between the two rails. Finding there was that there was an ineffective inspection regime for these areas, and this derailment, despite not causing fatality, caused massive disruption, as you can imagine, in the station throat of a sort of busy station into London. It was a catalyst for improving our track geometry measurements at S&C locations and at station areas, and resulted in the introduction of the multi-purpose vehicle with geometry equipment fitted to it. So this vehicle runs around the network, about 50 or so stations, key stations are covered to measure dynamic geometry, so under load, what the vehicle is feeling, seeing as it passes over the track. And it's been very successful in terms of providing that extra information that's just not possible to actually capture from static measurements or manual measurements of geometry, as Liverpool Street proved. There were attempts with this vehicle to effectively do the PLPR for S&C. They were largely unsuccessful in terms of adopting them and rolling them out nationally. But I'm going to cover a bit more on that later, because we've had greater success in the last couple of years in that area. And a presentation on infrastructure monitoring wouldn't be complete without a few images of the rest of the fleet. So top left, our new measurement train, still called our new measurement train, despite being introduced in 2002, 2003, and until a couple of years ago, still had the kit on it that I worked on when I was working at AEA Technology at the very start of my career. So pleasantly surprised that that equipment lasted quite so long. Yeah, I think we need a new name now. On the right hand side at the top is our mentor vehicle, our ill-fated mentor vehicle that was responsible for the firework display that you sort of saw in the previous video. Actually 1955 vehicle, so you know, very old. Real issues with keeping that vehicle in operation. It's currently out of service with a faulty component, and we're having to manufacture because parts are just obsolete for that vehicle. And yeah, also worth mentioning, bottom right, is our use of passenger vehicles to monitor the infrastructure. So number of systems fitted to passenger vehicles, both monitoring track and overhead line, and something that with the asks of our routes and regions for more frequent data and more coverage of our infrastructure, definitely an upward trend in that area. Okay, so going to jump forward to sort of 2020, fairly recent past, and talk a bit about our infrastructure monitoring program and some of the recent developments that we've managed to deliver as a result of the program. To start with, just want to sort of get things in context in terms of what the IM program is, why it's there, what we're doing. So fundamentally, routes and regions are becoming ever more dependent on infrastructure data, asset condition data. Their access to the infrastructure is reducing. The safety drivers for taking people out of dangerous environments rightly increasing. As I mentioned, you know, the fleet that we have is extremely old. New measurement trains, still 1970s technology. Definite sort of issue and risk in terms of continuing to operate and be quite so dependent on technology that's that old, and simply put, it's not delivering the service that our routes and regions need today. It's definitely not going to be able to deliver the service that they've asked for tomorrow and future control periods. Coupled with that, advances in technology, sort of ever increasing pace of development, both of sensors, and of data science in terms of exploiting data and extracting information from that, particularly in the area of video and machine learning and artificial intelligence, mean that all of that coupled together has led us to the point where a fundamental review, fundamental sort of transformation and reinvention of the infrastructure monitoring service is required. So the IM program was put in place to develop the vision, the strategy and the implementation plan to give us that service that's fit for the future. It became became apparent very quickly that the routes and regions aren't in a position to have a program come along, talk to them, understand their requirements, develop a strategy, deliver that strategy without doing anything about the current service and trying to trying to squeeze more out of what's currently running. There's huge opportunity, continuous improvements opportunities identified with the current fleet, with the current technology, even though it is old, even though there are challenges there. Definitely more to be done there was the sort of message that was coming across loud and clear. Definite appetite to do things quickly, definite appetite to work differently and consider things that even maybe has been discounted in the past, just to the sheer sort of pressure that they're under. So the program very quickly sort of split into two sort of parallel streams: do more with what we've got, and developing that future strategy and planning to deliver it. So I'm going to cover some of the quick wins that we've worked on and delivered over the last couple of years, and then I'll come back to the sort of future strategy and our planning and work that we've done to actually deliver or start to deliver that future strategy. When we spoke with our routes and regions, which we've done a lot, I think 500 or so hours spent with delivery units, maintenance engineers, asset managers, just to understand exactly what it is that they need, what their problems are that they need solutions to. There were some real key themes that consistently just kept coming back and back. If this was a non-virtual presentation, sort of real life presentation, might be a bit of a quiz opportunity here, but I'm not sure that's going to work virtually. So I'll just press on. First key ask: boots off ballast. Wherever possible, want to replace manual inspections with people in dangerous, hazardous environments with technology, whether that's camera technology, sensor technology, whether there's an opportunity to reduce the amount of visits to particular locations to inspect things or look at problems, verify faults. Real driver to remove all unnecessary or as much as possible boots off ballast. Part of the way of achieving that, people really consistently asking for photos with faults. So rather than just a wiggly line of a graph with a big spike on it showing you got a problem here, if you have a photo alongside that, gives a whole massive amount more context. You can understand, is it genuine? Is it likely to be genuine? Is it likely to be spurious? Maybe what the root cause is, maybe even going so far as to say what the fix might be. So might ultimately lead to like one visit to site rather than multiple visits to site. One visit to site armed with information, armed with a photo, you're more likely to find the issue. You've got an idea of what you need to do to fix it, so you can take the right things with you, is the thinking. And then kind of alongside all of that lot, so defects, not suspects. So rather than a whole list of things that might be wrong, much more certainty around the things that have a high probability or a high chance of being wrong. So back to the ultrasonic example, a whole load of suspects are issued to people to go and manually verify, trying to reduce that number. So trying to increase the ratio of defects to suspects. So much more of the things reported are genuine things that need to be fixed. We've been working quite differently, and I think hopefully that comes out in the examples that I'm going to give next. We've been working quite differently to achieve this. Part of that's sort of a program that's been put in place to actually look at this and look at the improvements that can be made, kind of separate to the day-to-day delivery of the service. Very easy with especially with an aging fleet and an unreliability sort of in that, to get bogged down in the day-to-day firefighting, get the train out, get the data collected, fight that fire, fix that problem. Difficult to then also look at how continuous improvements can be made or how incremental improvements can be made. Got a real customer focus in the program, really understanding what people want in the routes and regions and how we can best achieve that, how we can work together. And working together has been key to it. So involving people at the right stage, getting their feedback, getting their input, making sure that it works for them rather than getting to the end of something and saying, here you go. And actually something's been lost in translation and it's not actually solving the problem. Learning by doing is been a key thing. So, rather than going after perfection, sort of get something out there, work with it, improve it as we go along. Again, kind of links back into that customer focus, or customer involvement. Work with them, iterate, kind of don't go for perfection straight away. Get something out there and get it used and learn as we go. linked to that, kind of pretty much the sort of same pragmatism. So doesn't have to be perfect, doesn't have to solve the whole problem. If it delivers an improvement, if it stops somebody having to go out on track to do one thing, or one out of two things, they're still sort of halving the amount of things they need to do when they're out there, reducing the time then when they're out there. And I think one of the things, it's not really about how we're working to deliver it, but having an infrastructure monitoring program is that focal point. So lots and lots and lots of initiatives, lots and lots of work going on in this space, in routes, in regions, in TOCs, in Roscoe's, in the supply chain, lots and lots of things, inevitably sort of some overlapping, some leaving little gaps because they don't sort of align properly. Having the program as a focal point has been really good to bring together all of those different initiatives, set things on the same path, actually, get that community working together so that everybody's got a view as to what's happening and learning as we go and learning from each other rather than reinventing the wheel all the time. So just trying to work out how to get rid of this black box, but can't do it. So first example of sort of continuous improvement or quick win was improvements to our video service. So I'll move it down here. So improvements to the video service. So we've collected forward-facing video from our fleet for a number of years. Been largely quite a manual process, so physically removing data off the train, manually processing it and sending it out to the route customers on hard drives in the post. Crazy in 2020 or 2019 when we were still doing that. One of the first things we did in the IM program in conjunction with the AOS teams, transform that. So working with the supply chain, put equipment on there, upgrade the cameras to get good quality imagery, put equipment on the vehicles to transmit the data straight from the train into the cloud, and have a portal, log into the portal, be able to see the imagery there within minutes, 20 minutes, maybe an hour of recording. Massive step forward. I think, if I'm honest, probably one of the key drivers for this was actually COVID. So the first use case for this service was replacing cab patrols. So people sat alongside a driver as the vehicle travelled around, as a passenger vehicle travelled around the network, observing the infrastructure. Just wasn't possible in COVID, whereas this came along as a solution. Video data, watch the video data on the from the portal, and carry out the sort of virtual cab patrol, if you like. Very quickly grew into a whole load of other use cases on the right hand side there. Not going to go through them all in detail, but the one on the slide here, the image at the top, was a piece of work, a project I was involved with in preparation for and during the Commonwealth Games in Birmingham, which was looking at using forward-facing video to identify graffiti. So a real push to clean up the railway environment ahead of and during the Commonwealth Games. So forward-facing video used, machine learning model trained to spot graffiti, highlight that to the maintenance teams so that they can go out and remove it or cover it over. And as you'd imagine, sort of, as technology's moved on and sort of the pace, etc., of technology, there's a whole raft of use cases that are automatically now things spotted from the video footage. So different models looking for whether it's vegetation, signs, trespass, all detected. So as soon as the footage lands in the platform, all of those models are run over the data, and the things that are identified as spotted and flagged in the footage is shown on the right hand side of that image at the top. So lots of boots off ballast from that respect, and similarly with the next example, which is related. So also sort of video based. This one's more about bringing together different sets of data. So overhead line measurements, whether that's contact force or wire height or stagger, combining that with images from the pantograph camera. So whereas previously we might provide a list of exceedances, like you've got an issue at this location or that location, putting those locations, providing those locations to the video portal and stamping those locations into the video with bookmarks allows a user and an OLA maintenance engineer to go in there and literally step through the video footage, exceedance by exceedance, watching a small snippet of information, a small snippet of video to understand what's going on at that particular exceedance location. Is it a real genuine exceedance that something needs to be done about? What is it that could be done? And getting to that point where it could go out to site to fix the problem rather than going out to site to look for the problem and try to identify it. I think recent changes with red zone ban effectively make it very, very difficult to spot those types of exceedances, because it's just so difficult to stand by the side of the track rightly with trains passing. So having the link up between measurements and video footage has been critical in understanding some of these overhead line incidents. Unfortunately, need to cover off a couple more incidents, and this time three in total fatalities of Network Rail staff carrying out work at switch and crossings. So Margam in 2019 resulted in two colleagues, Gareth Delbridge and Spike Lewis, losing their lives. They were carrying out S&C maintenance when they were struck by a train. And then in 2021 February, Tyler Byrne was inspecting S&C and lost his life as he was struck by a train. So particularly difficult, still fairly recent history. If there is a positive to take out of that, it's been these events have been catalysts for improving our visual inspection of S&C. And the next thing I'm going to talk about is our Class 153 visual inspection unit. We've built a couple of visual inspection units using old passenger stock Class 153 diesel multiple units. Basically, great example of one of the projects, of the way we've delivered projects within the IM programme. Very much learn by doing. Got there from idea through to a vehicle being built and being trialled in service within 6 months. Had to work very differently with the supply chain and with our route and regional customers to achieve that. Something this programme was very much driven by our southern and eastern regions, and that help and that involvement and that sort of drive is really the reason why I think a lot of this happened so quickly. The systems on board the train, the sort of yellow boxes on the front of the train that are also in red boxes, are cameras that are looking down at the rails. There's lighting there for those camera systems, and then in the centre of the vehicle there's a forward-facing video and also an infrared video. Vehicle operates autonomously, so driver only, so all the systems operate autonomously. Nobody on the train switching stuff off, and checking it's working, taking data off. All of the data is wirelessly transferred off the vehicle. So autonomous from a measurement perspective, just driver to drive the vehicle. Some good advances in technology here, with particularly as our improvements in locational accuracy. So something that's critical when you're looking at S&C. 30 millimeters is the level of accuracy we've managed to locate all of the video footage, the geometry data through this project. And the way that this works is slightly different to PLPR. I'll show you a video in a couple of slides' time, just sort of showing that interface. Effectively, rather than having machine learning models and that pulling out candidates, the system uploads the video into a portal, and then an inspector can actually carry out a virtual inspection using the video. So they're responsible for looking at the various features, identifying the things of interest. What's different with this compared to when we've attempted to do similar before is that right at the start, it was acknowledged that we'd never be able to do 100% of what the visual inspection, on-track visual inspection does. And as a result, we've got now a hybrid regime in place where one inspection can be done with a train, and then the next one's a sort of physical on-track inspection. I think that way of working, that sort of openness to sort of work differently, is something that has definitely improved and evolved over the years that I've been working in this area, and is key to the success of initiatives like this. So I'm just going to play a quick video which give my voice a rest, and also shows you the inspection suite for the data from the 153 VRU. Just wanted to cover one part of the system on the 153. I mentioned about this, the accurate location. Really worth pulling that out. It's a massive development compared to where we're at the moment with location. So it's a system that's called rail lock, fitted underneath the vehicle. Effectively special type of cameras that actually mean there's no blur of motion blur on the images that are collected as the vehicle runs along. So it's looking down at the forefoot, and it's using the image that it captures, or the images that it captures, to identify these small little features within the images. So not features that you or I would recognise as features, or sleepers, or rails, or clips, or anything like that. Just sort of peculiarities or unique features of the sort of ballast. Where it's been described as effectively fingerprinting the track. So it's developing a unique fingerprint of each for each piece of the track. Does that during the mapping stage, which is the blue here. So this is the mapping stage, identifying those fingerprints, and then as the data is being recorded in the top bit here, it's mapping those features. So lining up that feature with the corresponding feature in the reference map to a level of accuracy of 30 millimeters, which is incredible, and has been a key part of the success of the system. Just want to cover just to keep a few points off here. This slide was put together 3 or 4 weeks after the vehicle had been introduced into service. Since been running for about a year, so quite a lot more confidence, quite a lot more shifts being covered, miles being covered, point ends inspected, and most importantly, quite a lot of boots removed from ballast. Excellent feedback from routes and regions. Excellent buy-in throughout the whole thing to actually make it happen from routes and regions, whether that's been getting involved in planning, make sure the vehicle runs where it needs to, or running the standards change process to make sure that the standards support the use of this hybrid regime that I mentioned, where alternate inspections are carried out sort of manually versus Trainborne. Okay, so jump into the final part of the presentation, looking ahead to the future, so CP7 and beyond. I think one key thing that keeps coming back, I keep mentioning continuous improvement. There's still 2 parallel streams in the programme, so we're not standing still. We're still continuing to strive to improve things for our routes and regions with the current set of data that we've got, the current trains we've got. Where we need to deploy new technology, we're deploying that technology. We're trying to deliver the future sort of as we go. So we're still exploiting existing technologies and data. We're still challenging ways of working, looking for opportunities to simplify things, looking for opportunities to simplify or challenge standards that where technology could lead to a better solution or a better way of doing things. Embedding the changes is key, and where we're ultimately heading is trying to become more proactive, get more predictive maintenance in there, and get away from the situation where we're reacting to faults and things being recorded by trains. So I've got a couple of examples I just want to cover before wrapping up. Back to rail defects. So mentioned previously about suspects and the number of suspects, sort of 40,000 or so per year. This graph shows a breakdown of some of those suspects. To get to the point where we're not having to go out and rectify or fix or replace the rail or do the weld repair. So this graph just shows a breakdown of the type of suspects, categorized by sort of root cause or category of defect. So surface damage, whether it's wear, deformation, or other like corrosion, or inherent through manufacturing. What's also important here is whether the defect type is generally visible on the railhead. So you can see from the graph, there's a large proportion of these types of defects are actually visible. Some are not, and some it's a bit undecided at the moment. So where we're heading with this again is kind of that photo with a fault. It's that combining data sets together. So remember the PLPR imagery that we collect, the high definition images. The way that things work at the moment is a suspect's reported, red cross, and then somebody goes out to track to manually verify that suspect. So walk along, pushing a walking stick with one of the role search units on it. They have to start 22 yards before the reported location of the suspect and end 22 yards after, to take account of sort of inaccuracies of GPS. Looking at this image, there's a whole load of features in that 44-yard section that could potentially be identified as the suspect. So there's a weld, there's another weld, there's also a small squat there. Here's the actual defect, so a vertical longitudinal split that you can see in the rail. There's some changes in fastening types. There's another weld, and there's a weld repair. So lots and lots of things in this image, but having the UTU data, having the image alongside it would have allowed us to understand that the root cause of this suspect here was this vertical longitudinal split. The thing that you need to go out and do is replace a section of rail, rather than go out and verify and then go back and do the actual action that needs to be done off the back of the verification. So this is an avenue we're exploring in combination with the accurate location. Having images and accurate location is a potential real game changer for rail defects and verification. As an example of areas we're looking to challenge current practices and improve the way we do things. Second one's around data, so bringing together different data sources. You remember on the initial detective coach video about overlaying traces, comparing the results from different trains against one another. Same problem, but just done digitally now. So I can remember overlaying traces on a light box, pieces of paper, sliding them one way or the other right at the start to line them up and look at changes. All done digitally within our Insights tool developed by Intelligent Infrastructure. This shows a year's worth of track geometry data. You can see the changes over time. What we then do is look at those changes over time and look at that rate of deterioration, which is shown in the sort of solid line there, and then predict the time to failure, so the dotted line. When's the data going to breach the threshold where action is going to be required? And prioritize that differently. So this table here shows prioritization based on time to fault. So how long have I got before a fault develops, rather than the old way of, or current way, sorry, of doing things where magnitude of fault is the only way of looking at things. Again, more about bringing together different sets of data. So in this example, work we're doing to bring together eddy current data, so rolling contact fatigue, crack depth, rail profile data on the right hand side, and rail depth data from the UTU system. So all of that lot combined gives that picture of rail health, helps us get to the point where we understand what treatment we need to take. Do we need to mill? Do we need to re-rail? Do we need to just do some preventative light grinding to get rid of the surface cracks? Similarly in the track world, so track bed information, whole load of data here, and just about see layouts of track, age of asset, type of asset, construction, data from core samples taken physically out on track, ground penetrating radar data, all combining to give that holistic view of the infrastructure, all combining to work out what type of treatment required. Is it tamping, stone blowing? Is it ballast cleaning, or do we need to do a full renewal with formation, drainage, etc.? What's the data telling us? All of the data being brought together. So, promise, very final part of the presentation. So, future. How do we do? Well, what do we need? What do we need to do? Well, where are we at with delivering tomorrow? How are we going to deliver what our customers want and need? They're firmly on board. They're pushing for change. They keep mentioning they're chomping at the bit. They want their data, they want it reliably, they want to concentrate on their day job, not worry about whether they're going to get the data they need and what they're going to need to do in case they don't get the data. A lot of the work we've been doing over the last couple of years, proof of concepts, delivering, we're trying to move from that way of Network Rail being integral to buying equipment, getting it fitted on trains, making sure it stays operational, making sure the data flows, into a different way of working where we're much more reliant on the supply chain to deliver services, measurement services, data services. We're seeing some really good success. I mentioned the 153 VRU unit. It wasn't Network Rail buying all the kit, doing all the design, fitting it. It was procured as a more towards a service, and that's the way that we're heading. The supply chain, they know what we want. They're working in a new way, and they're fired up and ready to go. They're chomping at the bit to get involved and deliver what we're asking them to. We've had we've had around 12, I think, pre-market engagement sessions over the last 3 months with groups of suppliers who have formed various groups, various suppliers in each group delivering various different aspects of the monitoring service that we're asking them to provide. Something that's coming loud and clear as we'd expect actually is sort of 2 more paths this time in terms of how the full service gets delivered. So we can't get away from the core need to have that core service. Those dedicated vehicles, some of the technology is quite slow speed, requires lots of water for rail testing particularly. It's something that doesn't fit naturally into the passenger timetable or even the freight timetable due to speed constraints. Some of the other asks from our routes and regions, high frequency, regular data at speeds that passenger vehicles operate, particularly thinking overhead line here. It's only realistically possible to deliver that from fitting equipment onto service trains. So we're heading down that hybrid sort of route to deliver the full set of requirements that our routes and regions are asking us for. And just the final slide, summary of where we're at. So timeline in terms of our procurement for the service of the future. As I mentioned, market engagement is underway at the moment. Finished our sort of focus groups with the groups of suppliers this week, checking the understanding of our requirements, checking their view on deliverability, understanding risks, issues, timelines, everything, so that the tender can be created in a way where it is deliverable, it is achievable. It's something that is not switching off large swathes of the market for particular, whether that's technical points that can't be delivered or contractual points that are unattractive. It is covering that whole end-to-end service, so provision of vehicles, provision of equipment, maintenance, planning of trains, operating trains, data transfer. It's exciting times, and very much looking forward to continuing to work in this area and deliver changes in infrastructure monitoring as we go. Thank you very much.
Kev, thanks very much for that. It's really interesting presentation. I think for me, the thing that really struck me is how we've seemed to get the software and the imagery so much better tied together than what I'd seen previously. Yeah, no, thanks for that, and thanks for showing us the journey you've been on and some of the challenges for the future.